Let's get one thing absolutely clear before we go any further. You would not survive on Saturn, not for an hour, not for a minute, not for a single second after arrival. There is no suit, no spacecraft shell thin enough to let you feel the planet. No technology currently in existence or on any drawing board that would allow a human being to stand on Saturn and live to describe the experience. Saturn is not hostile to human life the way a desert is hostile, or the way the deep ocean is hostile. Environments where survival is difficult, but theoretically possible with the right preparation. Saturn is hostile the way a nuclear reactor core is hostile, the way the surface of the sun is hostile. It belongs to a category of places that the universe did not build with anything like us in mind. And yet, and this is the strange magnetic quality that Saturn has always possessed, we cannot stop looking at it. We cannot stop sending machines to photograph it, study it, orbit it, and eventually plunge into it. We cannot stop dreaming about what it would be like to be there. Saturn occupies a unique place in the human imagination, a planet so visually extraordinary, so architecturally improbable, so utterly unlike anything in our terrestrial experience, that it functions less like a real place and more like a symbol of beauty, of scale, of the universe's total indifference to human comfort. So let us talk about Saturn. Let us talk about exactly why you would not survive it, and in doing so, let us come to understand something about what the planet actually is. Not the ringed jewel of astronomy class posters, but the genuine, staggering, annihilating reality of the sixth planet from the Sun. The moment you arrive. Imagine, for the sake of this thought experiment, that you have somehow crossed the 1.2 billion kilometers separating Earth from Saturn at its closest approach. You have survived the journey. Your spacecraft has decelerated. You are approaching the outer layers of Saturn's atmosphere, and through whatever viewport you have available, you can see the planet's upper cloud band stretching across the curved horizon. Ochre and gold and pale cream. Enormous bands of turbulent gas moving at speeds that seem lazy from a distance, but are anything but. You decide, in this thought experiment, to step outside. The first thing that would kill you is the atmosphere itself. But before we get to the chemistry, we should address the more fundamental problem. There is no surface to step onto. Saturn is classified as a gas giant, which is a term that sounds straightforward until you really sit with what it means. There is no ground. There is no rock. There is no solid layer anywhere near the accessible outer regions of the planet on which a human foot could conceivably rest. What Saturn has, instead of a surface, is a gradual, relentless thickening, an atmosphere that begins as thin, freezing gas at the upper cloud layers and descends over thousands of kilometers into conditions of pressure and temperature and density that transition through states of matter that do not have easy names in everyday language. You would not land on Saturn. You would fall into it. And you would keep falling, getting crushed and cooked simultaneously until there was nothing left of you that could be meaningfully described as a person. Saturn's atmosphere is composed primarily of hydrogen and helium, about 96% hydrogen and 3% helium, with trace amounts of other compounds including methane, ammonia, acetylene, ethane, and water ice. None of this is breathable. A human being dropped into Saturn's upper atmosphere without any protective equipment would die of asphyxiation almost immediately because there is simply no oxygen. Your lungs would fill with hydrogen. Your cells would be starved of what they need within seconds. Your brain, which can survive only a few minutes without oxygen before irreversible damage begins, would begin to fail almost instantly. But the atmosphere would not give asphyxiation the time to finish its work cleanly. The temperatures in Saturn's upper cloud layers hover around -178 degrees Celsius, colder than anything that exists naturally on Earth's surface, colder than liquid nitrogen, cold enough to freeze human tissue in moments. Exposed skin would not simply feel cold, it would begin to undergo frostbite at a speed that makes the word frostbite seem almost quaint. The moisture in your eyes would freeze. The fluids in your joints would begin to solidify. Your lungs, drawing in gas at that temperature, would sustain immediate and catastrophic damage. So within the first seconds of exposure, you would be simultaneously suffocating and freezing. This is already, by any reasonable standard, unsurvivable. But Saturn is not done with you. As you fell deeper into the atmosphere, and you would fall because Saturn's gravitational pull at its cloud tops is approximately 1.065 times Earth's gravity, stronger than you are used to, but not dramatically so. The temperature would begin to rise. This seems counterintuitive. You are moving away from the sun, descending into the depths of a gas giant. Why would it get warmer? The answer lies in pressure. Saturn generates an enormous amount of internal heat. It radiates roughly 2.5 times more energy than it receives from the sun. And as the atmospheric pressure increases with depth, the gas compresses and heats up dramatically. Within a few hundred kilometers of descent, the temperature would rise above zero, then above the boiling point of water, then far, far above anything your body could tolerate. The human body begins to experience protein denaturation, the breakdown of the molecular structures that keep cells alive and functioning, at temperatures above roughly 42 degrees Celsius. At 100 degrees, water boils. At several hundred degrees, organic molecules begin to break down entirely. Saturn's interior reaches temperatures of thousands of degrees. You would not freeze in Saturn's depths. You would cook. You would be reduced with extraordinary efficiency to your component chemical elements. If the temperature did not kill you, the pressure would. And the pressure on Saturn is a force so far outside the range of human experience that it requires some effort to even conceptualize. At sea level on Earth, the atmospheric pressure is approximately 101,325 pascals, 1 atmosphere. The human body is built to function at this pressure. It is calibrated to it in every detail, from the elasticity of your lungs to the way your eardrums flex. Descend to the bottom of the Mariana Trench, the deepest point in Earth's oceans, and the pressure reaches about 1,086 atmospheres. This is enough to crush unprotected submarines. It is enough to kill a human being almost instantaneously. It represents the outer edge of what engineered materials can withstand. Saturn's pressure at its cloud tops is already several times Earth's sea level pressure. 100 kilometers down, it reaches around 10 atmospheres. 1,000 kilometers down, it is in the hundreds of atmospheres. Deeper still, and Saturn is enormous, its radius nearly 10 times that of Earth. The pressures climb into the hundreds of thousands and then millions of atmospheres. At a few million atmospheres of pressure, something extraordinary happens to hydrogen. It stops behaving like a gas. It stops behaving like a liquid. It enters a state called metallic hydrogen, a phase of matter that does not exist anywhere on Earth's surface and that we have only been able to create momentarily in laboratory conditions using the most powerful compression equipment ever built. In this state, hydrogen conducts electricity like a metal. It behaves according to rules that belong to an entirely different chapter of physics. Your body would not reach metallic hydrogen depths. Your body would cease to exist as a coherent structure long before that. The pressure would collapse your lungs at relatively shallow depths. It would then compress every gas-filled cavity in your body, your sinuses, your digestive tract, eventually the cells themselves. You would be crushed with a thoroughness and efficiency that no industrial press on Earth could match. Let us return briefly to the upper atmosphere, to those cloud bands that look so peaceful from a distance. Because before the temperature and the pressure had their way with you, before any of those slower processes of destruction had time to run their course, Saturn's winds would almost certainly be the first thing to encounter you, and they would not be gentle. Saturn has some of the fastest winds in the solar system. Near its equator, wind speeds have been measured at approximately 1,800 kilometers per hour, roughly 500 meters per second. To put this in terms of terrestrial reference, the strongest tornado ever recorded on Earth produced winds of around 480 kilometers per hour, and it caused devastation on a scale that entire towns never recovered from. Saturn's equatorial winds are nearly 4 times that speed, and are not isolated storm events but the planet's permanent baseline atmospheric condition. At 1,800 kilometers per hour, wind is not something you lean into or brace against. It is something that disassembles you. The aerodynamic forces acting on a human body at that wind speed would not merely knock you over. They would produce differential pressure gradients across your body so extreme that your structural integrity would fail almost immediately. The same principles that make aircraft wings generate lift, the Bernoulli effect, the relationship between airspeed and pressure, would operate on your body with catastrophic results. You would be torn apart by the aerodynamics, and this assumes relatively uniform wind. Saturn's atmosphere is not uniform. It is a system of enormous storms, of lightning discharges millions of times more powerful than anything Earth produces, of hexagonal polar vortices so vast and so geometrically perfect that scientists spent decades debating whether the images were real. A hexagon at Saturn's North Pole, a standing wave pattern in the jet stream, each side larger than the diameter of Earth, has been rotating there, stable and precise, for as long as we have been observing it. Nobody fully understands why it is hexagonal. Nobody fully understands what maintains its extraordinary geometric precision over centuries. It is one of the many things about Saturn that sits at the edge of our comprehension, beautiful and baffling and completely indifferent to our desire to explain it. Saturn's moons, the places you might actually survive. Here is where Saturn becomes interesting in a different way, not as a place of destruction, but as a system of worlds. Because Saturn does not travel alone. It is accompanied by 146 confirmed moons, ranging in size from tiny captured asteroids barely a kilometer across to Titan, the second largest moon in the solar system. A world so substantial that it has a dense atmosphere, lakes, rivers, and a complex weather system. Titan deserves its own long meditation. It is the only moon in the solar system with a thick atmosphere, denser than Earth's in fact, at the surface level. It has a methane cycle analogous to Earth's water cycle. Methane evaporates from the surface, forms clouds, rains back down, flows into rivers and lakes and seas. Its largest seas, Ligeia Mare, Kraken Mare, are filled not with water but with liquid methane and ethane, sitting at around -179 degrees Celsius, colder than anything your body could tolerate. But the atmospheric pressure on Titan's surface is about 1.5 times Earth's, manageable, survivable with the right equipment. You could walk on Titan. You would need an insulated suit to handle the extreme cold, and an oxygen supply, since Titan's atmosphere is primarily nitrogen with methane and has no breathable oxygen. But you would not be crushed. You would not be boiled. The gravity is only about 1/7 of Earth's, so you would feel extraordinarily light. You could, in theory, strap wings to your arms and fly under your own power in Titan's thick, low-gravity atmosphere. This is not speculation. Scientists have done the math. Human-powered flight on Titan is physically possible. Then there is Enceladus, small, brilliant white, geologically alive in ways that continue to astonish planetary scientists. Beneath its icy crust, Enceladus harbors a global subsurface ocean of liquid water, kept liquid by tidal heating from Saturn's gravitational pull. From cracks in its south polar region, called tiger stripes, enormous geysers erupt continuously, shooting water vapor and ice particles hundreds of kilometers into space. This material forms Saturn's E-ring. Enceladus is literally contributing to the planet's ring system in real time. The water erupting from Enceladus has been sampled by the Cassini spacecraft, and what it found was extraordinary. Complex organic molecules, hydrogen gas produced by water reacting with rock, and silica nanoparticles indicating hydrothermal activity on the ocean floor. The same basic conditions that scientists believe gave rise to life on early Earth. Enceladus is one of the most compelling candidates for extraterrestrial life in the entire solar system. Not distant extraterrestrial life, not something we would need generations of interstellar travel to reach, but life potentially thriving right now, in an ocean beneath ice, orbiting a planet you can see from your backyard with a decent telescope. The rings, the most beautiful structure in the solar system. No discussion of Saturn is complete without confronting the rings, and confronting them honestly, not merely as a pretty image, but as the genuinely extraordinary phenomenon they represent. Saturn's ring system spans an almost incomprehensible distance. From the inner edge of the D-ring to the outer edge of the E-ring, the rings extend roughly 282,000 kilometers, about 73% of the distance from Earth to the Moon. If you could lay the ring system flat beside Earth, it would dwarf our planet entirely. Yet for all their vast horizontal extent, the main rings are extraordinarily thin, in many places only about 10 meters thick. The ratio of width to thickness in Saturn's main rings is comparable to a piece of paper. An incredibly vast, incredibly thin sheet of ice and rock, held in precise orbital geometry by Saturn's gravity and the gravitational influence of its moons. The rings are composed primarily of water ice particles, ranging in size from tiny grains to chunks several meters across. They are not static, they are dynamic, constantly evolving, shaped by gravitational resonances with Saturn's moons that create gaps, waves, braids, and structures of extraordinary complexity. The Cassini division, the most visible gap in the rings, clearly visible through a backyard telescope, is created by a gravitational resonance with the moon Mimas. Every time an object in that region of the rings completes 2 orbits, Mimas completes exactly 1. And the repeated gravitational tugs sweep the region relatively clear. And here is something that should stop you cold. The rings are young. By solar system standards, shockingly, disturbingly young. Analysis of data from the Cassini mission, which orbited Saturn from 2004 to 2017, suggests that the rings are somewhere between 10 and 100 million years old. The solar system is 4.5 billion years old. The rings have been there for, at most, 2% of that time. The dinosaurs were alive when the rings formed, or perhaps even after. In solar system terms, we are living through an extraordinary, fleeting moment, catching Saturn at one of the rare periods in its history when it wears its famous jewelry. The rings are also disappearing. Saturn's gravity is slowly pulling ring material down into the planet's atmosphere, a process scientists call ring rain. At current rates, the rings will be entirely gone within 100 to 300 million years, perhaps sooner. We exist in the narrow window of cosmic time when Saturn looks the way it does in every image you have ever seen of it. Future species, arising on worlds we cannot yet imagine, will observe Saturn as a ringless planet and have no idea what they are missing. On September 15, 2017, the Cassini spacecraft, which had spent 13 years orbiting Saturn, returning more data about the planet and its moons than any previous mission, fundamentally transforming our understanding of the Saturnian system, was deliberately commanded to plunge into Saturn's atmosphere. This was not a failure. It was a planned ending chosen for a specific reason. Cassini was running low on fuel, and mission scientists could not risk an uncontrolled drift that might eventually contaminate Enceladus or Titan, worlds that might harbor life, with Earth microbes that had hitchhiked aboard the spacecraft. So instead, they chose a controlled death. They aimed Cassini at Saturn itself and let the planet do what Saturn does to everything that enters it. In its final hours, Cassini performed a series of maneuvers that no spacecraft had ever attempted, diving through the gap between Saturn's innermost rings and the planet's upper atmosphere, a region never previously explored, too dangerous for any earlier phase of the mission. It sent back data continuously, measuring the composition of the ring gap, sampling the upper atmosphere, transmitting until the atmospheric forces overwhelmed its antenna pointing capability and the signal was lost. The entire mission team knew that Cassini was dying as they watched the data stream end. They had worked with this spacecraft for decades. They had built careers around it, raised families during its journey, grown old alongside it. When the signal cut off, several of them wept. There is something deeply moving about this, About the fact that we built a machine, sent it to the edge of the solar system, and then chose to destroy it rather than risk contaminating a world that might be alive. It reflects something important about how seriously scientists take the possibility of life on Enceladus and Titan. You do not sacrifice a billion-dollar spacecraft to protect a place you are merely curious about. You sacrifice it to protect a place you think might actually matter. Every time I think about Saturn, I return to the same fundamental problem, the problem of scale. Human beings are not built to intuitively grasp the sizes involved. We understand the difference between a mouse and an elephant. We can feel, viscerally, the difference between a room and a stadium. But the numbers that describe Saturn operate so far outside our intuitive register that we process them as facts without truly feeling them. Saturn's diameter is about 116,000 kilometers. Earth's diameter is about 12,700 kilometers. You could fit roughly 764 Earths inside Saturn by volume. The rings extend for hundreds of thousands of kilometers. The moon Titan is larger than the planet Mercury. The hexagonal storm at Saturn's North Pole has sides longer than the diameter of Earth. The geysers of Enceladus shoot material hundreds of kilometers into space. These are not metaphors. These are not exaggerations for effect. They are the measured, verified, peer-reviewed dimensions of a real place that exists right now, in the same solar system you were born into, orbiting the same star that warms your skin on a summer afternoon. And you would not survive there, not for a second. The planet that has captured human imagination since the first ancient astronomer noticed it moving differently from the fixed stars. Too beautiful, too ringed, too obviously special to be ordinary, is a place of absolute, total, comprehensive lethality to human life. It will crush you and freeze you and burn you and tear you and dissolve you into your component atoms without the slightest effort, without any awareness of your existence. Saturn does not know you are there. Saturn does not care. It has been doing what it does for 4.5 billion years, and it will continue doing it for billions more, long after every trace of humanity has vanished from the universe. The rings will disappear, the moons will shift in their orbits, the storms will rise and fall, and Saturn will remain, golden, enormous, ringed with a ghost of something that was once there and is now slowly being reclaimed. You would not survive on Saturn, but perhaps that is not the point. Perhaps the point is that Saturn survives, has always survived, will always survive, and that for one brief, flickering moment in the planet's long history, a species of small, fragile, warm-blooded creatures on a tiny rocky world nearly 1 billion kilometers away looked up and looked outward and saw it and found it beautiful. That, in the end, may be the only kind of surviving that matters.